So that's our first optimization technique. There's no questions, we can move on to our second optimization technique. Your book lists 10 optimization techniques. We're only going to cover, I think, 7 of them between today and next lecture, because I think some of them are not actually that important. But we're also going to cover some other ones which I think are important. OK, so next thing we're going to look at, the next optimization we're going to look at is how to deal with how to deal with read misses in the cache that have some data there that needs to get kicked out of the cache. So here we have our CPU, L1 data cache. Our next level of cache here, we'll say level L2 cache or maybe main memory. There's something in this cache at a particular line, and it's dirty in the cache. So the dirty bit is set. It has state we cannot throw out. We do a read, and it aliases that same location. And we need to evict that line or create a victim. In a naive implementation, we'd actually have to sit there and wait for all that data to go out to main memory while we go get sort of the next, while we go to do the read and get the data and fill it in. OK, that's not very good. We sort of have to wait for this evicted dirty line. We'll talk about that in a second. So the processor could be stalled waiting on writes. One thing you can do is actually have the read misses go beyond the writes, sort of past the writes and past the writes going out to the unified L2. But one of the problems here is you don't have that many ports onto this unified L2. You really only have one port out here, we'll say. So you can either have the load sort of pass it, but then you have to do this little dance that when the read data comes back or the load data comes back, you need to have a place to put it. So either at that point, you might need to wait for it to go out to main memory or go out to the next level of cache. So you can't really get around this. So you can say, oh, well, I'll try to get my load out early and just sort of worry about it later. Yeah, but that doesn't work if that load hits in your next level of cache. You need to access the next level of cache, and you're waiting for this data to go out because you need some place to put it. So the solution to this is we put a little buffer between our L1 and our L2, or L1 and our main memory, and this will hold writes or victims that go out from the L1 to the L2. And now we have some place to put the data. So if we wanted to do this fast, we'd actually do the load. We'd miss in our L1 cache. We'd send that request out to here. And then instantaneously, we would start evicting the line into this buffer. And the reason we can't evict it here is because the load's actually using that data right now, or it's using the L2 cache, we'll say. But we have some place to put the victim data. And when the load comes back, we can put it into the L1 data array. So this brings up a whole bunch of problems. Biggest one being, at some point, you actually need to transition from the write buffer into the L2 cache. You can do that if you have extra time. So you can just have some circuit here which checks. But then comes the question of if you need to do this a second time, what happens? Your second, let's say, load that has to create a victim, and this buffer's full. What do you do? Well, you can just stall and wait. That's a pretty good option. So this kind of what you're saying here is the probability that you have 2 victims generated in a very short period of time is low. And this is actually a scheme that people do use. They don't do anything special, and the first victim that gets generated goes into the write buffer. The second victim gets generated, just stalls the pipe. That's OK. You can have higher performance if you can have the subsequent read basically go beyond the write buffer here and start actually doing something in the memory system. And if you want to do this, you need to, just like what we did in the previous example, you're going to have to check this write buffer to see if the data is there. And that introduces complexity, because now your data can be here, or even farther out. So it's just more places to check. OK, so that's like the first half of write buffers. The second half of a write buffer, why we want to put a write buffer, is if we have a write-through cache. So we've been talking about write-back caches, which introduce victims. But if you recall, a write-through cache, every single store that happens gets stored into the data cache, the low-level L1 data cache, and it also gets written to the next level of cache, we'll say, because it's writing through. So let's say you have a write-through from the L1 to the L2. And one of the challenges with this is you might not have enough bandwidth into the L2 cache to basically take in every single store that occurs. So the solution to this is you actually put a write buffer here, which will sort of buffer up some of this extra store bandwidth. And we'll introduce a notion of a coalescing write buffer. So this is a extra addition to a write buffer here that'll actually merge multiple stores to the same line. So let's say you have a store to address 5 and a store to address 6 with a write-through cache. You don't want to actually have to write sort of 2 full cache lines out to the L2. Instead, what a lot of people do is they have coalescing write buffers. So there's one write buffer here. It might have multiple entries that holds a whole cache line. And that first store will push the entire cache line out into here. The second store will try to push the whole cache line out, but it'll notice it's for the same address that it already has in it. So it'll actually merge the 2 cache lines into one location. And what this does is it actually decreases the bandwidth that you need at the L2. Because it's very common in codes to write sequential addresses. So it's very common to, let's say, you're adding 2 arrays, the destination array, you'll actually just be writing address after address after address. And you don't want to actually have to go fire up the L2 for every single store that you do in that array operation if you have a write-through cache. So you can put a coalescing write buffer here to save bandwidth into your L2. So this is our sort of second technique, is having this write buffer. OK, so what does the write buffer do? Does it decrease our miss rate? Caches are the same size. Associativity is the same. Probably not going to change our miss rate. Miss penalty. OK, raise your hand here. Who thinks this affects the miss penalty? Some people are raising their hands. I think we should probably all be raising our hands, because that was really what we were trying to do with this whole write buffer, is to reduce the miss penalty. And the reason this reduces the miss penalty is when that read misses in here, it doesn't need to wait for the write to occur of the background data or the victim data. Instead, it can just have that happen in the background. This also doesn't affect our hit time. It may actually help our bandwidth. The reason it doesn't affect our hit time is our L1 cache just will still work the same way it worked before. You still can do loads and stores against that, and if you hit, it's fine. So it only affects miss sorts of things. Bandwidth, like I said, if you have a write-through cache, this might actually effectively give you more bandwidth if you have a coalescing write buffer.